All right, everybody, we're going to get this puppy on the road. Mike Shah, welcome back. Don't applaud or anything. Come on.
Thank you, everybody. Good to be back here. And today's talk is going to be a little bit of a continuation from a Dconf Online talk, but doesn't so much matter if you've seen that before. Doesn't so much matter if you've done graphics programming. Just want to kind of get you excited about thinking about D in domains where I think it's really useful. So anyways, there's the abstract about this. Here's me if you want to learn a little bit about me. But the real important thing here that's kind of neat here, I recently changed jobs. So, a little D community announcement at my university. Now at Yale University, I'm teaching my building game engines course in the D programming language. So it's, very exciting. The students, are really enjoying it. And for those who are at Dconf last year, I brought some students. And for those watching later, you can, see their perspective on, was it worth it? The short answer is yes, it was worth it from both student and my perspective. For productivity and all sorts of reasons that we're going to talk about. So last time I talked about some graphics, and again, the standard thing to do is use a API like OpenGL or maybe Vulkan or Metal or Direct3D these days, and render some object like this. So we discussed some of the bindings that are available, GLFW, rendering a bunny in the object format, and using other techniques like multiple rendering targets if you want to do other stuff like deferred rendering and kind of get into the fun part of graphics, where you can basically build a system that supports the artists building your game and so on. So again, sort of just part two of the previous talk here, just to, again, have the goal of really just getting folks or graphics programmers some motivation to give the D programming language a try. Again, I've done a lot of C++ work, both professionally, teaching, research, and now sort of, again, doing more and more D programming. And I've really just enjoyed the productivity benefits that I've found, and not really with any trade-off of speed, right? It's all running just on the GPU. So again, I found D really well suited for graphics work, and I hope other folks will, again, get excited about it. So here's a little demo or a screen capture, again, of a classic scene in graphics. This is called the Sponza. That's the sort of building, and then you've got the bunny, or most of the bunny there, in the middle rotating around, and some other objects here. And there's a little bit of lighting and some other stuff going on. And what's interesting about this is the size. It's 260,000 triangles, which is reasonable size. So it's a good sort of benchmark to see, are we running fast enough in this type of application? Is D generating fast enough code? The answer is of course, yes, it can handle this. Our GPUs can handle this, where a lot of the computation's happening. And it's also a purposefully sort of unoptimized data set here, meaning that the world or the object files that I've loaded are art assets that have all sorts of interesting issues. The textures need to be flipped. Sometimes they're not aligned. There's the actual model is made up of many different pieces of art here. So it was a really interesting challenge to try to put something together, go through that process of what you might do on, say, game team working with assets that are coming in on the fly, and sort of see how resilient is your system, your sort of pipeline of getting graphics into the scene here. Just diving in a tiny bit just to see what's going on here, or what's sort of interesting about this problem with a sort of simple scene, even as this here, just putting my sort of graphics hat on. You can inspect these scenes using tools or GPU profilers like RenderDocs, a pretty popular open source one. And basically what it does is it allows you to capture a snapshot or a profile of that scene. So you can see all the API calls, where your allocations were on the GPU side of things. Again, it works just the same if you're coming from a C or a C++ background on D here, this profiler here. And then, of course, your other profilers like perf and so on are also very useful in this sort of graphics stack. And of course, don't forget about D's built-in profiler, and I actually like using that tool a lot as well. Within this tool, RenderDoc, you can inspect the geometry and the data that you've allocated. I don't have to read it here, but there's a bunch of interesting maybe things going on here, some function calls, all the OpenGL calls for this example that are going on. So pretty standard stuff here. And you can see some outlines of the geometry and kind of debug things, which is nice. So anyways, what's sort of interesting about this scene, as I alluded to, is you kind of take this in or interpret this as two pieces of data. Again, the bunny sort of in the middle, of the picture, small and rotating there in the animated version, and then the world here. But again, scrolling through your profiler, you find that this world, the Sponza scene, that's what this castle thing sort of looks like. It's actually made up of 23, again, objects that are oriented in different ways. They've got different textures of different dimensions, and it's just a really interesting kind of data problem to try to solve. So you want sort of a productive environment to iterate and eventually solve and get the textures right and the lighting and so on. So again, here's the same screenshot, just a little bit bigger. And what's, kind of going through here, each of these different models here, you can see the 23 different pieces or some, the wireframes that make up that world there. Again, just sort of showing the different chunks of data here and what's collected as a object file. That's the 3D format. So not like the compiled binary files, but OBJ is the common static 3D format. Looking at this object file format was kind of interesting. And again, I talked about this a little bit in a previous talk, but the basic idea is you have a list of vertices or some attributes for the geometry that you parse through. And then they might be grouped in some interesting way. That's the second group here. So you have a list of the faces, sort of defining the connectivity between the geometry, and maybe even different materials here. I just think this is a really interesting problem, and it's kind of interesting how you get interested in this stuff. But trying to think about how fast you can parse through this data, because this would be an important part of, again, iterating very quickly and being able to see changes as maybe an artist gives you a new 3D asset that you want to see. What's really neat is you can parallelize this process relatively easy in some ways, or at least it became apparent to me having some experience of D and just having threads available in an API to do this, where I could maybe parse this list of geometry, that's this top section here, and then as soon as I encounter these sort of blocks here that have use MTL, which is a material or the image or texture data, you can actually start processing that in parallel as well. So if you have a large enough file where it's worth making that decision if you want to parallelize and kick off some threads, you can actually do that. And again, this was just some of the things that I thought were really interesting, having the experience with a deep programming language that just were apparent how I thought about the problem. It goes back to, even on the D language tour, you see dot parallel for parallelization. So it's in my head. I'm already thinking about these things, and it's easily accessible. So this is setting up a little bit of a larger experiment for me in the future of a large data set. I think it's something like 2 million triangles, the Caldera data set that I'm investigating now with some students to see just how fast can we load data, essentially. So again, if you're not interested in graphics, maybe you're interested in sort of the data side of this. How fast can you load your data? And some of the things we've learned about Dconf, pinning your memory and using fast I/O and these sorts of interesting things. Stepping back just for a moment to thinking about the sort of graphics engine and the design, it's just been, again, a pretty pleasant experience working in D here. Because if you think about the core sort of application loop for a graphics program, it's basically something that looks like this in the top right. You have run, an infinite loop that just keeps running and running and running. And you can break this and sort of abstract it into maybe an advanced frame or have some control over how things work here. Just really easy kind of abstraction here to set up your program and start thinking about how can I be productive? How can I structure something that once I have the core here is maybe a little bit extensible and interesting if I want to build a game or a graphics application. Of course, you probably want more power than to run through that loop and just sort of put everything there. So of course you can define an interface and have some sort of callback, which again, I really like having an interface that I can program into. I can have my classes here and make up some callback to maybe print something or have some action in my game or simulation that happens at the start of a frame or wherever I want these entry points to be. The D language allows you to program to an interface, which is really nice, self-documenting code, and works quite well. And of course, if you don't want to do callbacks everywhere, you can have an event queue or something like that as well to push events into. But this is just one example of a structure here. Some other interesting things, though, thinking about interfaces and programming to interfaces. More recently, I've started thinking about these projects that I'm doing using OpenGL to create portable graphics projects. And I wanted to start targeting the web, for instance. And for me, an easy path to do that was through Better C. So that way I can distribute graphics applications on the web for students and so on to see. As soon as you use Better C, one of the things you do lose is the runtime that's provided. Now, of course, that's by design so that you can basically target different devices. I got to thinking about this and searching around. I found Attila's project, Tardy, which was really nice, which basically lets you use runtime polymorphism without, you're just using structs here, which is really cool. So I've started developing something similar in that vein as well, which was a great thought experience and also showed the flexibility and the power of the language, which was cool. So now I can target web here with better C. And with that, now I can have my callback system and everything. So I'm not really sacrificing anything, and I'm getting all the speed, performance, and now portability for graphics applications. Okay, getting back to the graphics story here, I found a lot of just productivity gains in the realm of graphics programming here. Don't have to sell this crowd here, but maybe for people watching, or you can send this to somebody who's thinking about D or how to get involved. They're just little, tiny, in some cases, large life improvements here for programming. I try to keep a better blooper wheel, but these are some graphic experiments gone wrong here. There's, something wrong if you look hard enough at these pictures. Because graphics programming, sometimes you're just getting a blank screen. Sometimes the texture's, messed up. So you get lots of different, strange errors that you want to, iterate and fix here. So in that way, graphics programming can be a real challenge. And sometimes the graphics APIs don't offer many great tools for debugging. If you've done some OpenGL programming, you basically have GL get error, which gives you an error code. You might get a callback if you're using a later version and so on. But it is nice otherwise to be able to iterate quickly. As a graphics programmer, you have some tools for iterating quickly. You can, within a graphics API, just recompile your code on the fly. That's sort of like a hot reload system, you would call this, where you can just recompile the shader or the graphics driver in the sense of your application on the fly while your game logic is still running, for instance. Thinking about it from that side, another common thing you might do in a game, or is becoming more common, is to say, well, what if on the CPU side I write some D code and I want to sort of hot reload that side, and be able to just load in code that can execute maybe game logic code or your application logic, and you can certainly do that. So I came up with a little. I think this is my first take at a script here in this image here. The DMD compiler is really fast, so if you want to just reload in a shared library, you can do that pretty much instantaneously, or very, very close. And LDC and GDC have also used, which are also very fast for adding in little game code or simulations that we have here. So if you're able to do that and you have your little callback system, you can really iterate quickly on your graphics applications or your engines here. Now, if you're loading code and unloading code, you do have to take some care with memory and who sort of owns these resources. So those are a few of the gotchas you can read or talk about. But it becomes really nice. So all of a sudden, I have this system where basically I can have my game running forever and change things on the GPU side or the CPU side and just view the changes. And I know there is some infrastructure for this kind of stuff, or was previously at least in LDC2. Last I checked with dynamic compile. But otherwise, you could cook up some system like this in no time to compile shared libraries and just load them in. So these are really appreciated and kind of cool features. And again, maybe if you're not interested in games or graphics, maybe this will be useful in one of your systems as well to think about these ideas. So a few other handy things that have just sort of saved me on the iteration time here. D has support for contract-based programming here. So things like postconditions and invariants and so on have been very, very useful. I spent some time building a tiny math library for this application so I could rotate and move around and stuff. And basically, every time I get a NaN value for a float because I divided by 0 or did something silly, I basically want an early exit. So it's nice to be able to just do that, similar to what was just being discussed in the Lightning talks about carry flags, and basically getting some indicator very, very quick that something's gone wrong. And again, you should load in some new code or recompile and find the bug. So these were just some handy things here. D, as we know, or folks in this room know, it's very easy to template code, maybe too easy in some cases. So you get a little template crazy, I probably have. But being able to template lots of functions and add different constraints can be very valuable, especially when working with some of these APIs, these graphics APIs like OpenGL. So here's a simple example here. In OpenGL, you have different shader programs that are doing the graphics work, whether it's the geometry, we call that a vertex shader, working with vertices and transforming them, and a fragment shader, working with the pixels. So those are two of the types that you can have here. Now, if you're just working in the sort of C API, you basically have an enum that you specify, but if you put in the wrong thing, what's your feedback? Well, you might get an error if you query for it. So it's kind of nice if you can template for the type and put in some template constraint. Now, whether you enumerate these or write a little function that checks all the types is up to you. But again, that's just very nice for having some fast feedback. So again, maybe I've gone a little bit template crazy here, but it just kind of saved me from these silly errors. So for my OpenGL programmers, you don't see error 1280, right? And that's your only feedback because you have a wrong enumeration. It's much, much nicer to just not have this code compile and be able to check that. Okay, so getting towards the end here, a few more pictures and thoughts before we leave this little graphics experiment. I did some more porting of some of my C++ code, again, to the D language. Here's sort of standard. Here's a normal mapping example, some lighting, some experiments with instancing where you repeatedly draw things and animate them. And really the goal here for me is both from a teaching and also from a serious perspective, because I think D is a serious language for putting out commercial products and games and graphics applications. It's just to start generating a large library of sample code for other folks to draw on. So things like I'm working on a little math library that I'd also like to distribute, and also starting to take a look at Vulkan and talking with folks about what that looks like in D and if we need wrappers or bindings. So there's lots more to explore, but it's a really exciting space, I think, to be in the D programming language and working with these APIs. So the tool stack that I use for today, and I'll distribute my code that I have for, I use the Bind BC projects, which are excellent for just getting started and work on Windows, Linux, Mac pretty much out of the box. I have my own math library and also found InMath and the GL3N library is very useful for linear algebra. So you can use those. And kind of wrapping us up otherwise, again, there's a lot of different graphics APIs out there, and we have bindings for them, so you can check those out. If you watch the Lightning talks, Steve's talk, like Raylib is a great API otherwise for doing graphics programming. The GLFWD bindings are also excellent, which I was using previously. So there's a lot of great resources out there already for people to get started and to start doing work in graphics or compute. The high-level takeaways of this talk is, D for real-time graphics, I think, is an excellent win. For me, at the least, the productivity gains have been enormous. The safer code, the code that's being run is still being run very fast. It's the same GPU code, can use the same tools that I've already learned. So in some ways, it's been almost effortless and just a fun experience rather than wrestling with bugs and the less fun stuff with programming. So I hope this gives you some encouragement if you are a graphics programmer or thinking about it to try this out with the D programming language. You don't have to do the standard write everything in C or C++. There's many examples of games in D and other languages. So that's what I tell folks to make the brave decision and give it a try. And I think you could really build a nice tool stack here for a competitive advantage with the D language. So I'll add more graphic stuff to YouTube. That's my plug there. There's been, again, tons of talks here on games and graphics from folks that are in the audience here in the past for, again, commercial games or indie games, for fun projects, other game engines like Supreme Engine and so on. And I've given some other graphics talks if you're just interested on non-real-time graphics as well. So with that, that's sort of the case for graphics. There'll be some sample code available after the talk. And thanks for your time and attention. And hope you consider D for graphics.
Fun talk. Thanks. I had just a few questions, which will reveal my ignorance of your expertise, actually. Are mesh shaders going anywhere? Is ray tracing going to affect the architecture of game engines in your classes and going forward? And third, is there any benefit now that we have heterogeneous memory management to make it simple? Is there any benefit to having like compute shaders, like picking up decompute as an augmentation phase to, I don't know if the compute shaders are actually used in graphics or not, but those are the three questions. Mesh shaders, ray tracing, and utility of decompute, yes or no?
Yeah, so the short answer is sort of yes to all three. So mesh shaders are starting to appear. Not as much in OpenGL. I mean, there are some extensions like 4.6, but the new APIs, for instance, are working with mesh shaders for giving more power and sort of levels of detail for how much graphic stuff you can basically put on your card. So mesh shaders, yes, these are relevant things. Sort of goes with the second question too with ray tracing. Again, the modern graphics APIs and their pipelines are having actually specific shaders for things like ray tracing. So those are coming. I think they're here to stay. I think folks will find maybe other use cases beyond ray tracing, but definitely here. And as far as, let's see, the compute pipeline or compute side of things, if I understand the question, I mean, I'm thinking about compute in terms of new APIs like Vulkan, for instance, which has compute pipelines. I mean, OpenGL does as well. Yeah, definitely accessible. Definitely things I think folks are using. I think folks are trying to look a lot how to use compute, for instance, to just make it look like the regular language. So that would be interesting to see in D as well.
So I believe the question on Bruce regarding compute shaders is pretty important because I have seen an increase in the usage of compute shaders on the gaming industry related to cinegraph building. So this can bring like much better performance. So I would guess this is a thing to start thinking more about now.
Yeah, if I understand the comment, yeah, compute, I mean, yes to all three. All are important.
All right, well, thank you there.
Right.
Ready? Yes, we're ready. 5 minutes starting now.
Okay. So this talk is about a small improvement I made to my workflow in the last half year, I think. And it's a thing that I've been thinking about for quite some time, having in my daily programming with D. So how many of you are using on-the-fly syntax checking, at least in your everyday working experience with D? Okay. And how many of you are using VS Code, opposite to other? And how many are using Emacs and Vim? Okay, so it's about equal. So this talk, fortunately, the tool I'm about to present is completely agnostic of the editors. So there's not going to be any fights here, hopefully. So syntax checking is probably something we've been all aware of. It exists, and it's a very useful thing to have when you're developing. So it catches lexical and syntactic errors, and in the case also semantics. So if I mistype something here, you can see that in the bottom here, I got lots of errors. And this is the variant fly check with an extension in Emacs, which is very convenient because you can click and navigate in various directions here. And it's also, so this is a lexical error. This is often instant on large code bases. So the thing that I want to present to you is an extension of what kind of errors it catches here. So obviously lexical and syntactic and semantic analysis, something we want to have on the fly. But what about tests? There's been a couple of extensions to fly check that does this. When the idea is that not only does it do the checking via the -o- flagged via DMD, it also runs the unit tests and overlays in the output the result of those unit tests if they fail. So if I change the value here, we don't have any syntax error, but we obviously have something that fails the test, right? And this is not new. It's just that the diagnostics is, in my opinion, what I've seen quite new. So what happens here is that it shows you not only that what the line failed, but also what the expected and the actual value is, which is very, very useful. Moreover, what about if we change this to 0 and then remove this code? So what would we like to have in this case? Well, we don't have any coverage on our sources, right? So what if we save here? So what happened now is that what was executing was not DMD, but a wrapper script that I've constructed that basically compiles the code with -main, -unit test, -coverage, runs that test, parses the output of the LSD files, and converts that to compile diagnostics. And then you just feed that as an argument to your syntax checker instead of DMD. So this is completely agnostic to any editor. So under the hood, it does everything and presents the data the results as compiler diagnostics. The tool is available in my GitHub repo.
Question? All right. One question.
So the tool is, it's my name, Nordlow, NORDLOW-XDMD.
Okay, I've noticed that when you show the example when your test failed, you get an exact message with the comparison that failed with the values specified. When my test failed, I only get a message, assert failed. Is there anything
There's a flag for that.
The flag in the compiler?
Yeah.
Why did I not know about that? What flag is it?
Check action context. Search for that in the DMD manual.
All right. Let's call it there. Thank you, Per.
You're welcome.
I think I mangled the pronunciation. Sorry.